Welcome to Chapter 18 of And So Squircle. In this video, we're continuing with sphubical coordinate talk from last time and looking at volume elements for sphubical coordinates. As a quick refresher as to what I'm talking about here, we'll be spending this chapter computing Jacobian matrices, which in general, given a function, that function's Jacobian matrix contains all of its first partial derivatives. It's often denoted with this partial notation as well. When looking at n-dimensional volume elements, i.e. just the product of the differentials of the coordinates, we can essentially convert to another coordinate system by taking the determinant of the Jacobian matrix and multiplying it by the product of the differentials of the new coordinates. Intuitively, we take the determinant because the determinant encodes the local change in volume between bases. Also, it kind of looks like it cancels out, doesn't it? For examples of Jacobian determinants, we can take this map as a function that converts us from rectangular to circular polar coordinates, and compute the Jacobian matrix whose determinant is just r. This gets us that the rectangular area element dA is equal to r dr d theta. Another example is the volume element in spherical coordinates, for which that scaling factor is rho squared sine phi. Okay, so we want to do the same thing, but for sphubical coordinates. We could take our general conversion formula from last chapter and use this for shorthand and, So there's no way that I want to compute any partial derivative of this behemoth. It's a product rule mess. But I wouldn't be making this video if there wasn't some way around it. Instead of trying to take the conversion from rectangular to squircular, we ought to just take the conversion from circular to squircular, since the map to get between them is much simpler, and we already know what the rectangular to circular Jacobian determinant is. Let's keep using this shorthand for hype and proceed with computing the Jacobian matrix starting in 2 dimensions and working our way up. Remember that based on this map, the only derivatives we're really worried about here are the ones involving the radius relation, as the other derivatives will end up being trivial. So this is our Jacobian matrix, and thus the Jacobian determinant is just hype theta, which I think is very elegant. So the area element will be hype squared r base p dr base p d theta. For 3 dimensions, this is our Jacobian matrix, which again has a determinant of just hype 3 base p, as the only minor with a non-zero determinant is the one along the main diagonal. And using our knowledge of the spherical volume element, we get our sphubical volume element. It's a very similar story for the higher dimensions, although our matrix is now a lot bigger. But again, using expansion by minors, we can see that the determinant is also just n-dimensional hype, and thus the volume element for nd sphubical coordinates is this. I really love this formula for quite a few reasons. The first is simply aesthetic. We have the decreasing powers here. Maybe it does reveal something cool about volume generally, but I'm not sure yet. The next thing is that this reveals some nice intuitive properties of the radius relation, where we can first get this equation by just doing the partial derivative as we have been doing throughout this video, but actually knowing how to get between coordinate systems does give us this equation, which is really convenient. And that is ultimately the moral of the story today. Okay, there you have it. Bye!